Hey guys, Mr. B here, and in this video we're going to be going through chapter 12.2 on Newton's first and second laws of motion. So let's get started. So Newton's first law of motion, in general, his laws of motion, kind of came in place due to a couple of different scientists. The first one we have here is Aristotle. Okay, now he was an ancient Greek scientist and philosopher. He made a lot of scientific discoveries just kind of by observing and making logical deductions, okay, but he didn't really do any experiments or really set down any evidence to kind of support his stuff. He just kind of thought about it and was like, yeah, this makes sense. But he was kind of the one who sort of started to set down the idea of science. Then we have Galileo Galilei, and he was the first one that really started to do experiments to prove some of these different ideas that he had. He's famous primarily for discovering how gravity works. And what he would do is he would take these wooden balls and he'd roll them down ramps, and he would calculate how much they were speeding up by, right? He'd calculate their acceleration, and he was the one to notice that gravity causes objects to accelerate at a set rate as they fall. So he's kind of like the father of gravity. And then, of course, lastly, we have Isaac Newton, who most of you know is very famous when it comes to physics because he kind of set down all these different laws. He published a book entitled Principia, where he basically introduced laws of motion and how things work, and basically a lot of the physics we deal with today are all based on his ideas. So, all right, so his first law of motion is one we want to talk about, and this is one that most of you probably know the saying too. But Newton's first law of motion basically says that the state of motion of an object does not change as long as the net force acting on the object is zero. Or, in terms that you probably are familiar with, an object in motion remains in motion, and an object at rest remains at rest as long as the net forces acting on it are balanced. Okay, that's basically what this one is saying. So, this is sometimes called the law of inertia, and this is the tendency of an object to resist a change in motion. Okay, so inertia is if you are going forward and something wants to make you turn, your body wants to keep on going forward. Or if you are sitting still and something tries to move you, your body wants to continue to sit still. Okay, so inertia is the tendency of an object to just keep on doing whatever it was doing. So I have a little YouTube video here that we're going to watch that will kind of demonstrate this. Okay, now this is going to show a car crash. Okay, so you can see here in this car crash that this dummy is traveling forward, and as soon as the car hits the wall, the dummy's body continues to keep moving in the direction it was traveling, right? Because of its inertia. And it keeps on going forward, of course, until it hits the steering wheel. Again, this is what we call inertia. So, again, we see car hits, dummy keeps traveling forward. Obviously, here is when it stops because a force acts on it in the other direction, which would be the steering wheel as it pushes against the dummy. But it keeps going forward. We can see other things, too, continue to go forward. So if we watch, we can see that the car seat next to the dummy also continues to travel forward. We can see it here as it goes forward and then whips backwards. Okay. Again, this is called inertia. And this is the primary reason why wearing your seatbelt is important in a car. Because if you don't, your inertia will continue making your body go forward if you get in an accident. And without a seatbelt and airbags to essentially stop you, you're going to go flying through the windshield. And you're not going to have a very good time. Okay. So this is also the reason why if you are in a car and you go around a corner really fast, you kind of like get pushed into the side of the car, right? Like you're going forward, car turns, you're like, whoa, and you get slammed into the side of your seat, or you kind of get pulled sideways, and it's hard to right yourself. That's because your body wants to keep on going forward, but the car is forcing you to turn. And then once the car is going straight again, and your body's going straight, then you're able to sit up normal just fine. Okay, so, all right. So there's some practice problems here. Of course, we're going to skip past these. These are in the quizzes practice at the end. So let's just keep on moving. Now, Newton's second law. Okay, now this one is one that most people aren't as familiar with because it doesn't have a cool little saying like the first one does. But Newton's second law is talking about unbalanced forces and how they cause objects' velocities to change. So basically, in other words, Newton's second law deals with forces and acceleration, all right? So we're going to be talking about mass, force, and acceleration. The mass of an object is what we basically determine as the amount of inertia that object has. So when we talk about mass, it's of course how big the object is, how much stuff is in it. But the more stuff it has, the more matter it has, the more inertia it has, meaning the more difficult it is to change its motion. If it's sitting still, the harder it is to get it moving. If it's moving in one direction, the more difficult it is to get it to turn or change whatever it's doing. Now, Newton's second law is actually an equation. Okay, it doesn't, again, have a nice little saying like Newton's first law does. Actually, let's do this way. There we go. Newton's second law basically says that the acceleration of an object is equal to the amount of force being placed on it divided by the object's mass. Okay, so we have an equation that's set up like this. Acceleration equals net force divided by mass, or acceleration A equals F over M. There is one other way that we also write it, and let me see if I can get my, there we go. Another way you'll see it is at force equals mass times acceleration, or F equals ma. Okay, that's the other way that you'll see it. So both of these equations are the same thing. We've just rearranged the variables. Okay, so what does this mean? So here's an example. Okay, so imagine you've got a guy here and he has a basketball in his hands. And he's going to pass the basketball to a friend of his, and he just, he pushes it and throws it outwards. So he places some amount of force on this object, which has a mass that's relatively small. And of course, it's going to accelerate away from his body as it goes that way. Now, let's say that he were to do the same exact thing, but instead of pushing on a basketball to pass it, he pushes on a car. So now we have an object that has a very, very large mass. The amount of force that he's placing on this object is the same amount as he placed on the basketball, but we can see that the acceleration of the car is, of course, much, much, much less than it was the basketball. So basically what this is saying and showing is that if this guy wants to push the car and cause it to accelerate at the same rate that he did the basketball, he's going to need to apply more force to do so because the car has a larger mass. Okay, that's basically what Newton's second law of motion says. So in order to get heavy objects to move, you need to apply more force to them to get them to accelerate, or in order to change their speed, their motion. Okay, it's not too difficult to understand. I think it's mostly common sense. Most of you guys probably know that already, but there's an equation for it. So, all right. The last thing we'll talk about here is weight and mass. These are two words that are used kind of interchangeably a lot in our everyday language, but they do mean different things, and they do pertain to Newton's second law of motion. Okay, so weight, your body weight. Now, weight and mass, like I said, oftentimes are used in the same terms when we talk about them in a sentence in our everyday language, but they do mean different things. So your weight is a measure of force. Okay, it is a measure of how much gravity is pulling you down to the ground. Okay, that's what your weight is. So we measure weight in pounds, which is a measure of force. It's not the metric unit of force. The metric unit of force is the Newton. So you could measure your body weight in newtons, but here in the US, we don't use the metric system. We use our own system, in which case we measure force in pounds. Your mass, on the other hand, is how much matter is inside your body, which is typically measured in kilograms, okay, or grams. So mass and weight are usually very closely related because the more mass you have, the more weight you will have. But it is possible to have no weight. It is not possible to have no mass. And what I mean by that is this. If you went into outer space, you would have no weight. You'd be weightless because there's no gravity pulling on you anymore when you're out in space. Or at least if there is, it's very, very, very weak. So you're essentially weightless, right? You can float around. But you're not massless. There's still mass in your body. The only way for you to be massless, have no mass, would just be to not exist. Okay? So when you go up into outer space, your weight will go down, but your mass stays the same. Now we can calculate weight by using this equation. We can take your mass and multiply that by the acceleration due to gravity here on Earth, which is a set number. Okay, it is 9.8 meters per second squared. Now this number was brought up in the previous chapter, and it wasn't that important, but now it's going to be very important. Okay, so this is a number that you'll want to remember. It's going to be used a lot. Okay, I'm just going to let you know right now. So if we take your mass in kilograms, okay, we'll even put this in units, kilograms. Now let's make our text box a little bit bigger here. We take our mass in kilograms and we multiply that by the acceleration due to gravity, which is 9.8 meters per second squared. Again, let's make our text box bigger here so that it fits. There you go. If you take your mass in kilograms times acceleration due to gravity, 9.8 meters per second squared, you will get a weight in the units of newtons, okay, not pounds. This would be in the unit of newtons. If you wanted to get it into pounds, you could convert it into pounds. 1 pound is about 4.4 newtons. So the pound is a larger unit of force. So if you weigh like 100 newtons, or if you weigh 100 pounds, that'd be like 444 newtons, okay? But either way, this is how you can calculate your weight. If you were to go on the moon, which of course has much weaker gravity than Earth, you could calculate your weight. All you'd have to do is take your weight, your mass in kilograms, and multiply that by the acceleration due to gravity on the moon, which is only about 1/6 of that of Earth. So you would weigh a lot less. Okay, so hopefully this gives you an idea of the difference between weight and mass and how to calculate it. You'll notice that this is basically Newton's second law of motion, right? We're just taking force multiplying by acceleration. So F, right, is basically F equals m times a, right? F equals m times a. That's how you calculate your weight, which is the same thing as Newton's second law. So, all right. Anyway, that is it for this section of notes. Hopefully that was helpful. As always, though, if you have any questions, make sure you reach out to me, and we can sit down and go over it more thoroughly. All right, guys. Thanks for sticking with me. I'm Mr. B, and I'll see you in the next one. Bye.